Welcome to Pomodoro Joe for Monday, July 10th, 2023. Today we're doing LeetCode problem 111, minimum depth of binary tree. This is an easy problem. So, given a binary tree, find its minimum depth. The minimum depth is the number of nodes along the shortest path from the root node down to the nearest leaf node. Note, a leaf node is a node with no children. So in this example here, we have our root node, which is 3. Then we have our first node to the left, which is 9. And this is a leaf node because it has no children. So this would be, I think, maybe 1, 2, or it might be just 1, depending on how they count it. Or we could go to the right, and it's 20, and then 15, and 7. And these are also leaf nodes down here, but they take longer to get to. So I think we would return 2, 1, 2. Let's see. Yep, we return 2. So the root node by itself would be 1, its children would be level 2, and then so on and so forth, according to their counting system here. All right, seems pretty straightforward. So we'll put 25 minutes on the Pomodoro timer and we will get started. So for problems like this, it's probably easiest just to go with a recursive solution. So the recursive solution would be to look at our current node, check to see if it's a leaf node. If it's not a leaf node, then we will go to the left and go to the right, recursing, calling the same function on the left and the right nodes. So this becomes the new root node, and it will check to see if it has any children. It does not, so then we will return back up to our initial call, and then we'll return. All right, so for this, we'll need our base case first. Anytime you write a recursive solution, you need to write your base cases. So the base cases, I guess we have a couple base cases. One base case. What if we don't have a root? Now, I don't actually know the answer to this one, so we might want to check to see if there is a test case for that. There is not, so let's add our own test case here. And in this test case, we're just not going to have anything in our tree. And in fact, let's do another test case where we have just the root node in the tree. All right, let's do another test case, and we'll just have some root node. All right, cool. So we have 2 custom test cases. Now for our root, if the root is none, if we don't have a root node, let's do this base case first. Well, I think we'll return 0. I don't actually know. They might want us to return infinite or -1. They don't say that here, so I assume we'll return 0. Okay, so this is our first base case. Okay, so that's the first base case. What's the next base case? Well, if we actually get to our leaf node, that's our final base case. So for that, I'll say if our root.left is none and the root.right is none. So this tells us here, a leaf is a node with no children. So if it has no left node and it has no right node, then this is a leaf node. So for this, we'll just return 1. I'm pretty sure that's correct because we would have 1 at the root node and then 2 for this leaf node. So we'll return 1. All right, so we've taken care of our base cases. If we don't have a root, we'll return 0. If our root node happens to be a leaf node, we'll return 1. Otherwise, for example, in this case, we are not a leaf node, then we will have to check our left and our right branches to see if those are leaf nodes. And if they are leaf node, then we'll take the minimum depth leaf node. Okay, so let's have 2 options. So the left branch option will be a recursive call on this min depth. So we actually have to call self.min_depth here because this is part of this solution class. So we have to call self.min_depth. And for the root, we'll just pass in this root's left branch. All right, and then the right option, again, that'll just be self.min_depth for the root's right branch. So the left option will tell us how deep we have to go on the left side to find a leaf node. And the right option will tell us how deep we need to go on the right side. So of those 2 options, we want to choose the minimum option because we're looking for the minimum depth. And we also have to add 1 to that because we are coming from some node above those 2 nodes. So we have to add one more layer of depth. So down here, we'll just return 1 plus the minimum of our left option or our right option. Okay, so this is kind of covering it. There's a couple edge cases I'm not covering. So for example, what if we don't have a left node or a right node? So they don't show an example here. I think actually maybe one of our cases here. Right, so here's a case. This root node does not have a left node. It only has right nodes. So I might try going down this left node. I'll hit this base case and return 0. Now that's not going to really be true because this doesn't have a left node, so that's not really a leaf node. We actually do need to traverse all the way down. So we better make sure we have a left node or a right node before we call this left option and right option. So if we have a left node, then we'll get the left option. And if we have a right node, then we'll get the right option. Now these are only going to be valid inside this if. So this is being declared inside this if statement, which means it doesn't exist out here at this scope, which means we'll have to declare this left option outside of this if statement. And we need to give it some default value. Now we already know that we're looking for the minimum option. So we want to make this left option huge so that if it's not actually a valid option, it won't be picked up in this min. So let's make this infinite. And we have to do the same for the right down here. Okay, so I think this should cover it. So we have our base case. If we don't actually have a root node, we'll return 0. We should never get into this case when we make our recursive calls because we only call recursively if we actually have a node. So this is really just for our special test case here where we didn't have any node at all. All right, next, if we have a leaf node, so this root doesn't have a left or right child, then we return 1. So that's the example where we have just our root node. We would return 1. All right. Then we have to look at our left option and our right option. So if we make it past this point, we know that we have at least one left or one right or both left and right nodes. So we know that one of these options will be the right answer. Then we return 1 plus the minimum of our left or our right option because we have at least one more step to go. That's coming from this root node going to the left or right nodes. All right, let's give this a try. Okay, this seems to work, and it passes our special test cases here, where we have no root, it's 0, and we have just a root, it's 1. Okay, let's submit this, see how we do. And we pass. And we do okay, not great, but we do all right. We beat 35% for runtime and 21% for memory. So we could definitely come back here and clean some of this up. So one thing we could do, for one, I think I want to swap this. This is less likely to ever happen. So let's put this after our more likely to happen base case. All right, then this one down here, this min, we can make our own minimum function call here. So let's do this. So we'll be doing our own min calculation here. So this will be 1 plus the left option if the left option is less than the right option. Otherwise, it'll be 1 plus this right option. Okay, let's try that. Oh, so I actually do need to put this one first. That's fair. I should have recognized that. We'll have to grab this, move it back where it was. All right, try that. We actually do worse. 30% from 30 down from 35%. So yeah, significantly worse. All right, so this was the recursive solution to this problem. We could also do this iteratively. And to do this iteratively, we can basically use a queue or a stack to keep track of which nodes we'd still need to visit. This would be very similar to your traditional graph traversal. Sure, let's do it. Why not? All right, so we'll replace our recursive calls here with an iterative function. or just a while loop really. So we'll have a queue, and this will represent our node and the depth that it's at. So this will start at the root and it will be at depth 1. Now while we still have some nodes, we'll grab a node out of the queue. Now we'll check to see if this node is a leaf node. So if this is a leaf node, then our depth, which will be actually, let's see, this will be node comma depth. So our queue will actually have a tuple where the node is the first value and the depth is the second value. So we have node and depth. We'll pop that out. If the node left is none and the node right is none, then this is a leaf node and we can return our depth. Now I'm doing a breadth first traversal by popping 0. So the first one that we run across that is a leaf node should be our depth. Better make sure that this is a node. All right, and then similar to our recurse, we're going to have to push our child nodes onto our queue. So if we have a left node, we'll push the left node at depth +1 onto the queue, and same thing for the right. All right. And now we should at some point jump out. We don't need another return down here. So this should cover it. All right, so for our iterative solution, we will start with a queue. We'll push our node and the depth onto the queue. Then while we still have some nodes in the queue, we will pop a node out along with its depth. If we actually have a node, which we should, then we'll check to see if it's left and right or none. That means it's a leaf node. If it is a leaf node, then we can just return that depth because that should be the lowest depth or the minimal depth that we can reach. Otherwise, we'll push our left node onto the queue and our right node onto the queue along with their depth, which is depth +1. All right, let's try this. Yep, I need to wrap these in tuples. All right, try that. Okay, so this works. Let's see if this does any better. And this does significantly better than our recursive solution. Now we're at an 89% for runtime and an 89% for memory. That's way better than our recursive solution. All right, let's see if we can push this just a little bit to get our 100% or get above a 90%. I think we can remove that because we're already doing this checkout here. We should never queue something that is empty or none. So let's try this. All right, so this might save us just a little bit to push us over the 90%. That actually drops us down. All right, undo, undo. Okay, the next thing we'll try is making this a deck. So a deck is a double-ended queue. It is actually optimized for pushing and popping. So if we create a deck instead of using our standard list, this should go a lot faster. And instead of doing pop 0, we have to do a pop left. So this might give us just the boost we need. And that does not. Man, all my tricks are failing. There we go. I don't know why, actually. So, by using the deck and removing the continue, we were able to get above a 90%. We're at 92% for runtime and 91% for memory. So that is the best solution I can come up with today. So that is it for me, and that was LeetCode 111, minimum depth of binary tree. We explored two different types of solutions. One was recursive, the other was iterative. In the iterative solution, we used a queue and we used a deck, which is a special type of queue for just this type of situation, and we were able to get a 92%. All right, well, that is it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.